Welcome to the last talk in this room. The title on the program is Symbolic Assembly using Clojure to Metaprogram Bytecode. And hopefully 40 minutes from now, more of these words will have meaning if they don't have meaning to you immediately. My name is Ramsey Nasser. This is where I live on the internet. I'm a game designer, I'm an educator, a Clojure programmer, and a programming language nerd. I'm just sort of really enjoy hacking on compilers and thinking about programming languages. And I want to thank Clojure West for accepting this talk. I have a friend who pointed out that I practice a form of TDD, which is talk-driven development, which means that I tend to get stuff done when I have a talk to give about it. So a lot of deadlines were met for this talk. So thanks for having me. So the subject that I'm going to talk on, I've given a couple of talks before that were much deeper dives into the technology and the theory of symbolic assembly and bytecode metaprogramming. There's about 3 hours of me waving my hands on the internet talking about this stuff. But in the limited time that I have today, I'm going to be sort of giving you all just an overview and an intro to this subject. And I'll try and provide links to these talks if you're interested in getting deeper into it. So metaprogramming bytecode. So what I want to sort of define the word bytecode here, because this is a little bit of a loose term. Really what I'm talking about is a low-level target language. So bytecode gets used, bitcode gets used, assembler gets used. It really depends on the platform that you're targeting. But generally, you'll have some kind of lower level target that you're interested in. So maybe it's an actual machine, maybe it's a virtual machine, and that target will have some kind of language that it natively understands. An actual Intel machine will understand x86 machine code, for example. The Java virtual machine understands JVM bytecode, and so on. So this is a talk about wrangling those lower level instructions and generating them. Now, why would you want to generate a code in a lower level language? The most immediate answer is you might be writing a compiler. And a compiler's basic job is to take source code that a user prepares and convert it into some other language, generally speaking. In practice, it tends to be language that's suitable to be run on some kind of target platform. This is a Clojure function and a snippet of the bytecode that it gets compiled to on the Common Language Runtime, the C# virtual machine. The technique that I want to share with you today is not, strictly speaking, limited to compilers, but I'm going to be focusing on compilers because they're the most immediate, they benefit the most immediately from what I'm going to talk about. So just a show of hands, who here does compiler work? A couple of people dabble in compilers. Who here recognizes this book? All right, great. This book to me is the most telling example of the perception of compiler development in the software engineering community. It is a dragon poking its head out of a computer at a programmer in shining armor. The dragon, in case you didn't get the metaphor, is tattooed with the phrase complexity of compiler design. This is not a fluke. So this is the second edition of the book. The dragon is now wearing a t-shirt that says the same thing. So writing a compiler is perceived as this intractably hard thing to do, right? And there is a lot of irreducible complexity to writing a compiler. You're trying to reconcile human thought and intent with the semantics of some target language, and that's just, a lot of that is just hard, and there's no trick that'll just make that go away. This is my favorite quote from the compiler development community. This is one of the GCC developers saying that trying to make the hippo dance is not really a lot of fun. And he's talking about maintaining GCC, the older C compiler that a lot of Unix tools use. I feel that a lot of the pain of developing compilers comes from the fact that they're built in weaker languages with sort of deficient semantics, like C, C++. APIs are mutable, they're object-oriented, iterating is very slow. So developing, you're kind of trying to tackle a hard problem using weak tools. And I think that's where a lot of the pain comes from. This is taken from the Clojure compiler on the Common Language Runtime, C#, just as an example, to be a little concrete about what I just said, of what compiler development tends to look like. You'll see a lot of ilg.emit calls. Does everyone see those? An ILG, in this case, is an intermediate language generator. And that's what you use to generate runnable bytecode. And you get an intermediate language generator from a method builder. And you get a method builder from a type builder. You get a type builder from a module builder, which you get from an assembly builder. If you don't have all of these things, you can't even begin talking about bytecode. There's no way to reason about the code you're generating abstractly. You have to set up this entire framework to just start spitting them out into memory or onto disk. And once you've generated them, you can't really query what opcodes you've generated. You can't take them back once they're put out there. You have this mutable object that you're just sort of changing in place and trying to get it right. So hopefully that's a sort of glimpse into what making the hippo dance looks like. And I know this from experience trying to hack on compilers and trying to improve them. And it ends up being really, really hard. So the approach that I find myself taking to hard problems is just how do we throw functional programming at it? And then the question is, how do we rephrase the problem of generating target code as a functional problem? And that is the sort of the idea here. And we're going to look at some concrete examples of libraries that I've built that use this. But the general idea is that if you can represent your target as data, as inert functional data, you can then use a functional language to manipulate that data, to structure it however you want to or need to, and then only at a last step generate actual runnable code from that data. That, if you can approach compiler development or code generation like this, it just turns into functional programming. And you can use a REPL. You can, things become testable. All of the properties of functional programming that people in the Clojure community, I think, agree are good, just emerge from that. And I present it here as a general idea because it really could be applied to any functional language targeting any kind of target low-level code. But the first concrete example of that I want to share with you all is a library that I built called Mage. Mage stands for the Morgan and Grand emitter. And it's the first sort of implementation of this idea of building symbolic assembler. Mage is named after the cross streets of the studio in Brooklyn that I was working at when I built it. This is the corner of Morgan and Grand. This is the Kitchen Table Coder Studio, where David Nolan is a member, and a lot of the sort of foundational thoughts or theory behind this came out of conversations that I had there with Kovas Baguda, who's a friend of the Clojure community. It's also named after how you feel when you're just generating bytecode from the REPL. This is a photo of me from earlier today. Just sort of took my armor off. So Mage is a symbolic representation and an emitter for the Microsoft Intermediate language, more informally known as C# bytecode. So Mage fulfills steps 1 and 3 of that earlier slide. Mage provides you with a functional representation of bytecode on the Common Language Runtime, the C# virtual machine, and it provides you with a way to take that functional representation and generate real bytecode from it. So why the Common Language Runtime? I think it's a really interesting VM in general, especially now that Microsoft has open sourced it and acquired Mono. It has value types. It has real generics, things that the JVM, I think, struggles with. It has very low overhead interop with C. So there are a lot of things about it just as a VM that I think make it an interesting target. How many people here knew that Clojure runs on it? That's good. That's getting better. I've had interesting theories in the past about people wondering how we got code to pipe to the JVM and back to the CLR as fast as we did, and like not knowing that there's a version of Clojure that runs. So there's a reader conditional, it's a real Clojure. A man named David Miller has been maintaining the port for many years, and it's quite a good port. And it's this version of Clojure that me and my collaborator Tim Gardner built a library called Arcadia on. Arcadia integrates the Clojure programming language with a game engine called Unity, which is scripted in C#. And Unity is an industry standard game engine that exports to every imaginable gaming platform. And we basically just wanted to make video games in Clojure. And fast forward 3 years to me talking about bytecode at Clojure West. So there's already a community of people using Arcadia to make games. This is a wacky, procedurally generated skateboarding game called Proc Skater that Joseph Parker and Ryan Jones made last year. So Arcadia exists, it's usable. Clojure on the CLR exists, and it's very usable. People are making things with it. But the bytecode that it generates isn't always the best. And it could be better. And for games, we really do need every last bit of performance. Which is what brought me to start investigating better bytecode generation on the CLR. So that's why I'm particularly interested in this VM. So what does symbolic bytecode look like? I think it's easiest to start with an example from real bytecode. So this C# method compiles to the bytecode that's listed below. So this is a method that takes 4 floats, multiplies the first 2, multiplies the second 2, sums them, and returns their square root. And just to make things interesting, it casts them to a double implicitly, if you could see the return type there. Now, the bytecode reveals a lot of the semantics of MSIL. It's a stack machine, so all the instructions are run against an imaginary value stack that I haven't really found a good way to visualize it. You kind of have to just imagine it. So the first thing that happens is load arg1. So the VM will load the first argument onto the value stack. And then after that, load arg2 will load the second argument onto the value stack. So now there are 2 values on the stack, the first and second argument. Mul will pop 2 items off the stack, multiply them, and push the result back on. And so on and so forth. The other arguments are loaded, multiplied, and by the time we get to instruction 7, there's just the results of the 2 multiplications that we add together. And then finally, we call the function. That's what a function call looks like in bytecode. And then that value is returned. So this is, yes? Oh, conv R8. That is convert into a real with 8 bytes, so cast to a double. It's kind of like the matrix. You start seeing it after a while. It all blends together. Yeah. So what does this look like as symbolic bytecode? This comes out of a MSIL disassembler. This is what it'll give you back. So now I've moved the bytecode to the top, and the symbolic bytecode is now on the bottom. You see that it is a mechanical translation from the real thing to the symbolic thing. And so this is a little different from other similar projects like Terra or Timothy Baldridge's Mjolnir, which are also techniques or libraries to metaprogram lower level representations, but they kind of bring their own ergonomics and semantics to the game. Mage, the rule in Mage is if it's not in the spec, Mage doesn't get it, basically. And there's a couple of reasons to that. It makes translation very easy. There are some situations when writing a compiler, I'll wonder what would C# do in this situation? And then I'll just ask it. I'll write that C# code and transcribe the bytecode. And you can do that because there's a one-to-one mapping. So symbolic bytecode here is this vector of invocations that I'm calling constructor functions. And we'll see what they return on the next slide. But you see that load arg1 becomes il/load arg1, and so on and so forth. The interop / method, that's just doing a reflective lookup to find a function pointer to the method with that name and that signature. So this is a REPL session invoking those forms one by one. You see that load arg1 evaluates to a Hashmap that is namespace qualified, keywords to values. Mage core opcode, load arg, and Mage core argument 1. This is what I mean by the representation of bytecode as data. I could look at this hash map, I could print it out, I could put it in a vector, I could do whatever I want with it. There's no way to reason about bytecode on the CLR like this. There's no, they're not tangible things that you can move around. And you see the result at the bottom of the interop method call. It's just this sort of pointer to an object. Oh, and the opcodes are mapping to enumeration values that print nicely. They could be keywords too, but the CLR actually gives a nice representation just for the opcodes, not for the full instruction. So Mage does a little more than just wrap the bytecode. Mage will wrap all of the structural elements of MSIL, including, so bytecode lives in a method body, and a method has a signature and a name, and a method has to exist within a type, and a type has to exist within a module and an assembly. It's a very verbose VM. But Mage will wrap all of it, and if we evaluated this, you'd just get nested hash maps and vectors. This is all just Clojure data. You can construct this however you want. If you look at the top, there's an emit-bang function, which takes your symbolic form and produces the equivalent bytecode. So this is step 3 in the symbolic assembly structure. And this is the very effective Clojure technique of pushing mutability to the very edges of your system. So the edge of the system here is there's only one emit-bang function, and you just call it at the very end. Everything leading up to that is just functional programming with functional data. So you'll see that I have some C# code printed in the bottom. The MSIL bytecode is actually so rich that a lot of disassemblers can infer the quote-unquote original C# code from it. So this is a C# code that no human ever wrote, but a disassembler just kind of guessed. And sometimes it's a little bit more terse to look at the C# disassembly than the raw bytecode disassembly. And I'll use them somewhat interchangeably in the next couple of slides. So a few more examples of the kind of intricacy that something like Mage allows for. There are no conditional statements or loops at the level of the bytecode. There are only branches to labels. So labels are represented symbolically as well. The IL label function will generate a hash map with a unique symbol. You see that the gensimmed label symbol is different for each one of these invocations. And then what you do to generate jumps, is you use Clojure let bindings to generate a label in one place and then pepper that value throughout your bytecode. So here, this is a method that, given a number, if the number is greater than or equal to the current year, it'll return the string the future. Otherwise, it'll return the string the past. So it loads the first argument. It loads the constant 2017. It compares the two to see if the first is less than the second, pushing the number 0 or 1 onto the stack. And then we branch if true to past label. And these two will have equivalent values. So we're leaning on Clojure's equality semantics here to be able to structure our bytecode. And if we don't branch, we return the future. Otherwise, we return the past. An example of something that is taken care of for you that's very nice. Notice that when we look at the bytecode, the BR_true instruction isn't branching to some nice symbolic or abstract representation. It's jumping to an address in memory, effectively. It's jumping to an offset, an instruction offset. Having to manage that manually is the hippo starts to show up again. Right? This is what you don't want to do. So being able to describe the shape of your bytecode abstractly is very, very powerful.
You can write down the list and calculate the number of bytes in each opcode?
Basically, yeah. The C# emission machinery will do that. Mage doesn't actually do that. So I'm very grateful to the men and women at Microsoft. So state is similar. If you want to generate a type that has a field, fields can be represented symbolically. and you see that there's additional metadata for the kind of attributes that this field should have. And again, using Clojure-let bindings, you can sort of generate your field in one place and pepper it throughout your code. So this is a type that has a mutable field with a getter and a setter. So this is an idea that I got from conversations with Cobos to not dabble in binding forms because they're extremely complex, but instead leaning on Clojure and Clojure's power to use its own binding forms to construct the bytecode that we want. Local variables also work in the same way. Instead of IL field, it's IL local. So this is just an example that you wouldn't use in a compiler. This is just a raw code generation example, just for completeness. A lot of repetitive code can be just generated using metaprogramming. This is bytecode that'll generate a type that will have an addition, subtraction, multiplication, and division method for every pair of numeric types on the CLR. So you see that we construct a vector of all of the numeric types on the CLR. We use list comprehension to generate every pair of numeric types. And then we invoke this binary method on every single one of them. You see that binary method is a function that takes a var and returns a function that takes two arguments that will be the first and second type, and returns the requisite bytecode to generate that method. And you see here, op will be replaced with add, sub, mul, and div. And I couldn't fit it on a slide, but it generates all of that. So there are files in the Clojure runtime that have these massive manually maintained brute force files of for numerics and other things. And if nothing else, this is less lines of code, and this is a little bit easier to maintain. So that is a very sort of quick intro to Mage. And Mage is sort of tames the common language runtimes in immediate language, but it doesn't really do more than that. Magic, which is the next library that I want to show you all. Magic is the what I've been calling the Morgan and Grand iron Clojure compiler. And it's an example of what the kind of symbolic assembly that Mage does enables. So this is an application of that approach. You could also think of this as step 2 in the original slide with the 3 steps to symbolic assembly. This is the do some functional programming part. Morgan and Grand, again, the library is named after the cross streets of my original studio. Iron is this traditional name, this traditional prefix that's used for dynamic languages that run on .NET. There's an Iron Python, an Iron Scheme, an Iron Ruby. This is my Iron Clojure. The name is also an excuse for me to just use this GIF in every talk that I give. I'm working up to it. So this is the architecture of the compiler. Its goal is to compile all of Clojure eventually. Not quite there yet, but it's getting there. And like any Lisp compiler, it takes your sort of S expressions, it passes them through an analyzer. Magic uses Niccolo Mometo's tools analyzer, which is an excellent Clojure analysis library written in Clojure. I wrote some additional CLR-specific passes for CLR types and host-specific semantics. But the analyzer produces what's called an abstract syntax tree, and we'll see what that looks like on the next slide. The abstract syntax tree describes the sort of semantics of the source code. Magic takes that tree, and Magic's job is to take the syntax tree and produce symbolic bytecode that Mage can then pick up and turn into runnable code. So this is the sort of 10,000 feet view of the compiler. So this is what the analyzer looks like. Is the font sort of big enough? A little small? HTML? So the analyzer, given a function that takes one argument and returns that argument, will analyze that to a Hashmap. Every form that it analyzes will have a Hashmap with different contents, but every Hashmap will have this op keyword, if everyone sees that on the third line from the top. That sort of describes the Hashmap. This tells us that, oh, we're looking at the analysis for an FN form. Different forms will have different op keywords. And then the function that turns an abstract syntax tree value into bytecode is symbolize, which is on the bottom, which may not be a great name. I keep sort of agonizing over this. Maybe manifest is a better name, or realize. I don't know. It's called symbolize for now. What? Conjure. Ah, right. See, stay on brand. Yeah. So what symbolize does is it takes this abstract syntax tree value, which is this hash map describing a form, and it takes a hash map of symbolizers, which we'll see on the next slide, and its job is to return symbolic bytecode. And you see that the lookup it's not a multi-method, but the op keyword is looked up in the hash map of symbolizers in the AST arrow function. And we'll talk about why it's not a multi-method a few slides from now. This is a conscious design decision. And then this is what the hash map of symbolizers looks like. It's a map of op keywords to symbolizing functions. And this is the hash map that's built into the compiler. So the thing to keep in mind is, so symbolizer takes an AST node and a hash map and gives you symbolic bytecode. And the hash map contains op keywords mapped to symbolizing functions. It's the basic architecture of the compiler. And as we look at some examples, it may be more apparent why I've constructed it that way. So the simplest symbolizer is the const symbolizer. So a const node is any literal value in your source. So an integer, a string, these will be analyzed to hash maps whose op is const. And if you start reading at the bottom, you see that the const symbolizer just extracts the val key from your AST. So this will be the actual value of the literal, and it passes it to load constant. Load constant is a multi-method that switches on the type of the value, and for a string, it'll return the symbolic bytecode LD stir, which the CLR has an intrinsic load string opcode. For integers, it'll return a LDC I4, load constant integer 4 bytes. And it need not be single value, right? This is a function. So for a Boolean, if k is true, you load the value 1, otherwise you load the value 0. So this is an example of building compilers functionally and the organizational power that you get. You can use Clojure's multi-methods, namespace semantics, all the stuff that you love about Clojure to organize your code. You can start breaking down the generation of your bytecode that way. This is a little bit more involved. This is the do symbolizer. So the semantics of do in Clojure are that the body, every expression in the body gets evaluated, and its return value is discarded, except for the last one, right? The return value of the last expression in a do is the value of the whole expression. So what do does is it interleaves, using Clojure sequence function, it symbolizes each statement and then cleans up after it using interleave, except for the last statement, which is ret. The analyzer actually separates them out for us. So this is another example of using Clojure's sequence tools to construct bytecode however we want, but also an example of the symbolizer map being passed through. So you see that the do symbolizer, it gets the hash map passed in as a second argument, and that hash map gets passed into its body. So we're threading this map through the whole compilation. And an example of why I want to do that instead of multi-methods follows. But I need everyone to take a deep breath, because this is All right. So this is the symbolizer for let bindings. And this looks like a lot. But I will say that this is the entirety of the logic for arbitrarily nested let bindings in 27 lines of Clojure that fit on one slide. I had to zoom out a little, but it fits on one slide. In other compilers, this logic is spread out across a bunch of places. So there's a terseness here that's actually very, very, very exciting. And I do a deeper analysis of this in my other talks, but I just want to briefly point out why the sort of threading of the symbolizer map is interesting and valuable. The challenge in a let binding is that you need to create and assign local variables at the beginning of the let binding, and then at any point in the body, those locals may be referenced. And you need to connect the bytecode locals that you created in the beginning to their reference at the very, very heart of the body. And making that connection is an interesting challenge. And some compilers have used global variables, and there's all kinds of stuff. What Magic does is every let binding sets up a binding map. That's at point 1 in the code. And the binding map here is just a map of unique names of locals to their actual symbolic bytecode representation. And then the let symbolizer creates its own symbolizer map. That's at point 2, the specialized symbolizers local. It overwrites the local symbolizer with this function. It's an anonymous function that says, OK, if I encounter a local somewhere down in my body, and if that local's name appears in the binding map, then emit a load local for that value, that symbolic bytecode value. Otherwise, we sort of recurse up. We just symbolize with whatever symbolizers we got. So you have this chain of closures maintaining your local binding state. And you could look at it in one place. And I think when I got this to work, I sort of started to feel that this was not a complete waste of time, because this was really, really exciting. And this works and it nests arbitrarily deep. But this is also why I don't use multi-methods, because I want to be able to intervene on the compilation logic as it's flowing through the program. Another place where that shows up is the way optimizations work. Optimizations aren't hard-coded flags in Magic. They're just functions that replace the symbolization logic of certain ops. So in order to do intrinsics, Magic can actually replace certain static method invocations with low-level direct bytecode. And what that looks like is we replace the symbolization of static methods with logic that looks up the method in the intrinsic map, which we'll see on the next slide. And if there's some intrinsic bytecode for that method, we symbolize the arguments, convert the arguments, and spit out the intrinsic bytecode. Otherwise, we just use the old symbolizer. And then this is what the intrinsic map looks like. If you see a float cast to an int64, replace it with a convar4. If you see an array length, an RTA length to an array, replace it with a load length and convert it to an int. So this becomes very sort of declarative and a very straightforward way of intervening on the way the bytecode is being generated. Again, none of this is possible. What makes any of this possible is the fact that we can talk about this little snippet of bytecode abstractly, not attached to any method, not attached to any type, just sort of hold on to it and do with it whatever we want. On the suggestion of my collaborator on building Arcadia, Tim's, Magic is designed to be usable before it's finished. And I want to show you some examples of that, and specifically what it's being used for. And I've been thinking of it in terms of using Clojure in the inner loop. And that basically means being able to use Clojure in places where performance is extremely critical, and any kind of sloppiness is really not allowed. So Magic can actually exists side by side with the stock Clojure CLR compiler. So you could write a normal Clojure file, which is the namespace here, and use a magic define to create a magic function that lives alongside the rest of your Clojure code, and it's bidirectional. Magic can call code from the stock compiler, and the stock compiler can call code from Magic, but Magic will generate the absolute fastest code it possibly can with all of its optimizations for the function that you've passed in. So as long as you stick to the subset of Magic that's currently supported, you can start to build out your functions like this. This is an example of some code that Tim's is working on. So as far as I'm concerned, this is code in the wild that Magic is able to compile. Another fun macro that's a little cheeky is called faster. Faster lets you wrap arbitrary expressions, not even whole functions, and it will replace them with a static invocation to a method that implements, that sort of has compiled all that code via Magic. So if there's some code that's not running super fast, you can make it faster. And this allows you to use features of Clojure that Magic doesn't support quite yet, like anonymous functions. You see that in the filter expression, and still take advantage of some of Magic's power. An example of sort of inner loop Clojure is, I mean, in many cases, we'll save something like 52 bytes of garbage per function, which doesn't sound like a whole lot. But when you're building a video game, you're going to want to use that function potentially on many hundreds of objects. And in this case, we calculated, we were generating 26 kilobytes of garbage per frame using that original function to animate these cubes. And that's just one function. And the garbage comes from the fact that the compiler will move things to the heap when it really doesn't need to. And Magic is a little better at avoiding that. So Magic will compile functions that don't allocate any garbage if they don't need to in the best case, which makes this kind of Clojure usable in really tight areas. So I want to wrap up with some future work and sort of to the point of this being a general approach. Most of my work is on the Common Language Runtime and C#. But this next thing that I'm working on which is working as of Monday, is what I've been calling the Symbolic Assembler, or Symba. So it is very young and very, very new. But the basic idea is to do a Mage for LLVM. So symbolic representation of LLVM bytecode that you can do to LLVM what Mage and Magic do to C# and MSIL. And this is a screenshot of, this is some snippets of it working. Much like Mage, you have LLVM has a modules, and inside of modules there are functions with names and signatures. LLVM is not a stack machine, it's a register machine, so things are more tree-shaped. But this is a function that will compare the first and second parameters for equality and return their sum if they're equal, otherwise return the second parameter. That evaluates to a nested Hashmap, much like Mage. Fed to an emission function, it compiles to LLVM. And LLVM is very exciting because of its many backends. It can compile to machine code. It can compile to GPU code. It'll run basically everywhere. Its optimizations are also kind of unbelievably good. So this is the unoptimized compilation. And I'm going to jump to the optimized one. Watch this one line. So in the unoptimized one, in this branch, we add the first parameter to the second one if they're equal. LLVM will make the observation that, oh, you're adding two things that are always equal. You may as well just bit shift it one to the left. That's faster. And that, my eyes kind of went wide when I saw that, and I realized the depths that this thing is capable to optimize for. So this is very, very fresh, but this is, I feel like this approach can be applied to LLVM too, and there's a lot of exciting things that can be done there and built on that. All this stuff is open source and online if you want to check it out, and I'll be around if you all have any questions. Thank you.